Hello, everybody, and welcome back to the Energy Systems Engineering Zoomcast. This past week, we had the pleasure of being joined by Nikhil Kumar, Managing Director at Intertek. Nikhil's webinar was titled Electrification as a Cornerstone of the Energy Transition. In his webinar, Nikhil delved into the opportunities and challenges posed by electrification and the decarbonization of our supply chain. Renewable energy looks like a promising addition to our grid that will offset carbon emissions. However, it's not without its challenges. The more renewables we add, the more flexible we need our generation to become. Before we dive in, I'd like to provide a little background on Intertek. Intertek has 44,000 employees that perform over 340,000 inspections and technical visits per year. The company audits products, the trade industry, and raw materials in 100 different countries. Due to its global involvement, Intertek has seen drastic changes in the past few years as our society pushes towards a greener future. And in theme with that greener future, we've seen between 2012 and 2022 alone, there's been an increase of 8% in the world's population's access to electricity. As the world continues to develop, we'll see a greater and greater increase in electrical demand. Furthermore, electrification will double or triple our existing demand. We must take great care to ensure that the future is clean and that we electrify with purpose. To do this, Nikhil recommends we engage stakeholders, focus our investments, and then electrify equitably to raise our standard of living for all. Nikhil focused on India's energy transition as an example of a country entering the industrialized world. India is one of the largest synchronous interconnected grids, with coal generation still dominating 70% of the supply. Not surprisingly, India's GDP has climbed in tandem with their annual energy generation. Continuing to industrialize and raise the standard of living for a country is great, but India and the rest of the world needs to be cognizant of our future generations. We cannot continue to dump CO2 and methane into the atmosphere without facing serious repercussions. It's well past time we move to a cleaner future. So, how do we incorporate renewables? Well, Intertek examined just that in a study they performed for PJM. Their study focused on the impact of large-scale wind and solar on load balancing within the territory. Intertek began with hourly production simulations with up to 30% renewable penetration, overlaid transmission analysis to understand the capacity on the grid. They also examined the increased strain on power plants as they cycled more to compensate with the fluctuation in energy production. Cycling also increased carbon emissions because the plants run less efficiently as they're being turned on and off. Intertek made sure to take the added carbon emissions into account as well as the increased cycling costs. After all this was done, they could understand the market impact of the increased cycling and intermittent renewable generation. Intertek concluded that there was no insurmountable operating costs with lower system-wide wind operation. Furthermore, each scenario had lower coal and combined cycle natural gas generation, lower emissions and pollutants, and no unserved load. All in all, adding renewables to the grid is looking promising from a technical standpoint. However, there will be pain points along the way. As combustion units are asked to cycle more, their operating costs will increase. While the wear and tear on these assets will increase, the revenue from generating less electricity will decrease. The country has seen this problem before when natural gas first replaced oil-fired plants. The oil-fired plants become stranded assets because they were too expensive to operate. If legislation forces grid operators to take renewable power first, we may see our flexible generation become stranded. Although the total operating costs may be lower, profits will not be equally allocated. To counter this, the energy markets need to be reworked to reflect the benefits flexible generation offers to the grid. Another point not covered in the study is the addition of new combustion plants. This study focused on operating costs, as fuel served to be a large portion of operating costs for traditional assets. Renewables, on the other hand, do not have fuel costs. Therefore, their installation costs can be easily offset throughout their lifespan. However, adding more renewables will require the replacement of flexible generation as our grid as our generation assets continue to age. If the margins on these assets keep getting tighter and tighter, building replacements may not be viable. Unfortunately, our legislators are not politically incentivized to think this far into the future. So we keep kicking the can down and down the road further, slapping renewables on as a band-aid to try to meet our carbon goals. And then by the time, 2030, 2040, 2050 rolls around, we're going to have some serious issues relying on all of these old flexible generation assets to pick up the slack of renewables. Hopefully by then we've gotten our act together, but we'll just have to see. After all that, I'd like to pass it over to Omu so she can discuss Intertek's findings on power plant cycling costs and emission analysis. Over to you, Omu.
Thank you, Alex. To put this discussion together, I used the link that Mr. Kumar shared in his presentation. Power plant cycling refers to the practice of starting and stopping power plants or adjusting their output to meet fluctuating electricity demand. While this flexibility is essential for grid stability, it comes at a cost. The report categorizes power plants into 8 groups based on their generator plant type, such as coal-fired, steam, gas-fired combined cycle, and others. One of the significant findings discussed in the report is the variation in cycling costs between individual units and each type. Factors such as design, vintage, age, and operation and maintenance history can influence these costs. The report presents historical data on cycling costs, including hot, warm, and cold start costs, forced outage rates, base load variable operation and maintenance costs, load following costs, startup costs, and heat rate effects. The analysis conducted by Intertek utilizes both top-down and bottom-up approaches. They use unit composite damage accumulation models, statistical regression, and real-time monitoring data to estimate the costs associated with power plant cycling. The data presented in the report represent lower bottom estimate of these costs. Moreover, the report highlights the non-linear relationship between emission and generation level during cycling operations. Increased cycling and load following of fossil fuel assets can cause units to operate at suboptimal emission conditions. Understanding this relationship is crucial for accurate emission analysis and to mitigate environmental impacts. The document also emphasizes the importance of considering power plant cycling costs when planning for maintenance outages. Increased cycling and load following can lead to higher operation and maintenance expenses, as well as increased risk of equipment failures and forced outages. In conclusion, the findings from this document and presentation shed light on the cost and environmental implication of power plant cycling. It underscores the need for careful consideration of these factors in power system planning and operation. By understanding the cycling costs and emission associated with different types of power plants, we can make informed decisions to optimize grid reliability, minimize operating costs, and reduce environmental impact. Thank you. Over to you, Alex.
Thanks, Uma. That was really well said. Mohammed, could you please give more context behind the cycling trends that we have already seen within our own grid?
Of course, Alex. The cycling concept of the power plant refers to the process of running power plant up and down to meet fluctuation demand. This cycling is particularly relevant when integrating renewable energy resources like wind and solar into the grid because their output are variable and depend on many factors like weather conditions. Cycling has various impact on the grid environment and power plant. For the conventional power plant, the traditional power plant, especially those fueled by coal and natural gas, are designed to operate most efficiently when running continuously and stable out. However, as more renewable integrating in the grid and come online, this conventional power plant being used to balance the intermittency of renewable by ramping their output up and down to match fluctuation in renewable generation. This increased cycling put additional stress on the equipment and reduced their efficiency. For the efficiency losses, cycling conventional power plant lead to efficiency losses because these plants are most efficient when operated steadily at the optimal output. Rapid change in output requires the plant to operate at less efficient setting, resulting in high fuel consumption per unit electricity generated and increased emissions per unit the output. Also, there is economical implications on this cycling. Increase the cycling can also have economic implications of the power plant's operator. High fuel consumption and maintenance costs associated with cycling can reduce the profitability of these plants, especially if they are unable to recover these costs through electricity sale due to market dynamic or regulatory constraint. When we are talking about the stress on the stranded assets, as more renewable energy capacity is added to the grid and conventional power plants are forced to cycling more frequently, this is a risk that some of these plants may become economically unviable or stranded assets. This occurs when the operating cost of the plant exceeds its revenue generating potential, leading to early retirement and decommissioning of the asset. Finally, the grid stability. Cycling of conventional power plant can also impact the grid stability and reliability. Rapid change in the output from conventional power plant to balance the fluctuation in renewable generation can pose challenges for grid operator for maintaining a stable frequency and voltage. So that understanding and managing cycling in power plant generation are important aspects of transition to a grid with higher level of renewable penetration. This requires carefully planning investment in the grid infrastructure and potentially redesigning market mechanism to incentivize flexible operation and support the integration of renewable resources.
Thank you, Mohammed. That was insightful. Ahmed, what challenges lay ahead of us as we push to decarbonize? How can hydrogen, carbon capture, and other technologies help us manage these hurdles?
Thank you, Alex. As we push to decarbonize our economy and the transition to a low carbon future, several challenges lie ahead. These challenges include technological development and scaling up low carbon technologies such as renewable energy source, solar, wind, hydro, energy storage, hydrogen production, and carbon capture and storage is crucial for decarbonization. Infrastructure upgrades. Transition to a low carbon economy requires a significant upgrades to infrastructure, including electricity grids, transportation networks, and industrial facilities to accommodate renewable energy sources, electric vehicles, and hydrogen infrastructure. Cost and affordability. Some low carbon technologies may still be more expensive than traditional fossil fuel-based alternatives, making affordability challenge for widespread adoption. However, continued technological innovation and economies of scale are driving down costs. Policy and regulatory frameworks, effective policies and regulatory framework are needed to incentivize investment in low carbon technologies, promote renewable energy deployment, set emissions reduction targets, and establish carbon pricing mechanisms. Public acceptance and behavioral change, overcoming societal resistance and fostering public acceptance of changes in lifestyle, consumption patterns, and energy sources are essential for successful decarbonization efforts. Intermittency and reliability. Renewable energy sources such as solar and wind are intermittent and may not always align with energy demand, posing challenges for grid stability and reliability. Energy storage technologies and demand side management can help mitigate these challenges. energy equity and social justice, ensuring equitable access to clean energy and addressing social justice concerns, particularly in disadvantaged communities disproportionately affected by pollution and climate change impacts, is critical for a just transition to a low carbon economy. Hydrogen, carbon capture, and other technologies can help us manage these hurdles in several ways. Hydrogen can serve as a versatile energy carrier and feedstock for various sectors, including industry, transportation, and power generation. Green hydrogen produced from renewable sources through electrolysis can help sectors with hard-to-abate emissions, such as heavy industry and long-distance transport. Carbon capture and storage technologies capture CO2 emissions from industrial processes and power plants and store them underground, preventing them from entering the atmosphere. Carbon capture and storage can help reduce emissions from existing fossil fuel infrastructure and enable the continued use of fossil fuel while mitigating climate change. Other low carbon technologies, such as advanced nuclear sector, bioenergy with carbon capture and storage, direct air capture, and enhanced weathering, can also contribute to decarbonization efforts by providing additional options for reducing emissions and removing carbon dioxide from atmosphere. By leveraging these technologies and implementing supportive policies and regulatory frameworks, we can overcome the challenges of decarbonization and accelerate the transition to a sustainable low-carbon future. Thank you.
Thanks so much, Ahmed. As you can see, there are a ton of challenges that lay ahead of us. It is possible to integrate renewables into our grid, but there's going to be a lot of pain points and a lot of hurdles along the way. We're going to have to rework our energy markets. We might lose some generation assets and cause further disruptions in the market, but it's all possible. So we need to work together to continue to make our world better for future generations. Thanks for tuning in, and we'll see you next time. Take care.